I was telling, there we go, great. I was telling some of the students at lunch that once you spend a little time in Africa, sometimes it gets in your blood, and it certainly has mine. And I'm looking evidence that this is the case. There's always something new to bring out of Africa. So the work I'm going to present to you today is a part of a major collaboration contributed with many contributors. I especially want to acknowledge a former PhD student of mine, Robert Lyons, whose work the final chapter of his thesis was just published last month in PNAS, 10 years after we actually got those cores. So I'd like to first say a few things about why we bother studying in the Great Rift Valley. In particular, include some comments about our own species origins in Africa, which is a very limited record, actually, and we believe that geoscientists can contribute to the understanding of that very fragmentary fossil record. I want to say a few things about the framework of the Rift Valley and the lakes that occupy this system, because these island ecosystems are very much controlled and change is forced by geological events. Biological change is in many cases forced by geological events in those systems. The bulk of the talk will be about the results of this drilling work and some of the geophysical studies we carried out in advance of the drilling, and I'll sum up saying a few things about specific climate impacts on some of these ecosystems. So just a short reminder, and this is probably familiar to you all here. This is a digital elevation model of the African continent, and in yellow, these yellow dots are the locations, the principal locations of hominin remains. So we can see that there's actually relatively few sites, and in fact there are relatively few samples from which we can study our ancient ancestors. I was at a conference a few years ago, a joint conference of paleoanthropologists and geologists considering scientific drilling for understanding hominin evolution, and there were some terrific vocal disagreements amongst the paleoanthropologists there. The geologists got along fine, and in one side conversation I had with the program manager, he said, well, that's because there are more scientists than there are specimens to study. In any event, we've got this complex, elaborate, really bush, not so much a tree that has us right on this one little branch up here, and it's ever evolving. There are a number of new things that have come out just in the past few years, which are forcing modifications to this bush or this tree. So this is the iconic marine oxygen isotope curve that we rely on for many different studies. I use this as an intro to a general public presentation I've given on this project. But this is the context within which we use to cast the history of our early ancestors, and we've undergone tremendous changes over this time. We started off with these very small-brained animals 6 or 7 million years ago. We've actually got a major enlargement in our brain cases just over this time period, over the past million years or so. So sort of the holy grail for some of us working in East Africa is to try to recover this full time frame from within the continent. It's important to remember that this curve, which shows these periods of stability perhaps, then long-term cooling, and then much increased variability, this is a global climate average, right, that we've recovered from ocean sediment cores. But it's certainly not a record of climate within the African continent, within the Rift Valley. And I think you can make the case that ice sheets and oceans and the high latitudes are very much overrepresented in this curve. But clearly it's the best long-term continuous record that we've got. But if we were to look today at the samples or the records we've got from within Africa itself, this is what we've got really. We've got very short and discontinuous or punctuated records of African climate. So our interest in drilling in African lakes stems from trying to reproduce or expand upon what we know from the oceans and bring that into the continental interior, because there are some very significant differences in climate forcing in those systems. Another thing I wanted to just remark upon, and it's much easier when I give this talk in the likes of Syracuse, is that that the variability, the seasonal variability that we observe in Africa is not of temperature so much, but it's of precip, right? That's the big change that we observe on a seasonal basis. So this is the vegetation index from August, and we can see that tropical rain belt, the ITCZ, is focused over just south of the Sahel region up through there, and then we see the opposite situation in the austral summer, where we have a lot of rainfall down here. Lake Malawi, which I'll talk about, is situated right in this position, so it actually experiences a single three-month rainy season, whereas sites right at the equator actually exhibit two rainy seasons as the sun passes overhead twice per year. In fact, the long-term records of climate change posit that we'll see changes in this wet belt over time. Perhaps we'll see expansion or contraction of the belt, or we may even see displacement of this belt farther south, for instance, when we have pronounced ice sheets in the high latitudes. So just bear this in mind. This is the big change we observe on a seasonal basis. Another important piece of context for our understanding of African climate changes is the physiography or the topography of the system. So we have tremendous high elevations in underneath Ethiopia, centered around Ethiopia and Tanzania, and also southernmost Africa. The Rift Valley itself, we break into two parts: the magmatically or volcanically very active eastern branch of the system, which extends from the Afar Triple Junction all the way down through northernmost Tanzania. And then there's the western branch of the Great Rift, which is mostly amagmatic, only a couple of volcanic centers here, and characterized or dominated by these very large lake systems and a somewhat more humid climate for the most part in this area. So one thing that's been characterized for quite a while is this long-term drying of African climate, especially northeastern African climate. The system has aridified over the past perhaps 8 million years. And so what our research hopes to do eventually is to further constrain this understanding. So there are sort of two different models for the cause of this aridification event, broadly speaking. One suggestion is that it was generated by the uplift of those domes in eastern Africa, which are largely driven by mantle plume activity in this system. This was a simulation, climate simulation, that was published 10 years or so ago, suggesting that, in fact, we've got much better penetration of wetter air masses into eastern Africa back in the Miocene, when we had much less topography in the region. The other alternative model for the long-term aridification of eastern Africa was a major change in the Indonesian through flow. In fact, that there might have been some reconfiguration of this island archipelago to really limit that through flow and to cool off the western Indian Ocean, which had a direct effect on precip in eastern Africa. So these are two different models for the very long-term variability in this system. And it's not really what I'm going to talk about today, but these much higher frequency changes that we observe are superimposed upon this long-term trend. And so these questions remain, or these hypotheses remain open for consideration. So this is just one suggestion or one model that's been proposed for one additional contribution for that high topography, that is a dynamic topography contributed by mantle circulation that has helped to promote this very high terrain in northeastern Africa. And this is probably responsible for several hundred meters of the uplift that we observe today. So a dynamic response from the very, very deep earth. But superimposed upon that, we see some very high frequency and very high amplitude changes. So we're hopeful that some of this drilling work, and this is just one phase in a long-term effort, this drilling work can perhaps better constrain these rhythms and the timing of those changes. Right. So let's look a little more closely at some of the specifics of the system, I'm going to mostly talk to you about this basin today, Lake Malawi, but it's just one of the Great Lakes of the Rift Valley. These are enormous systems. They're really inland seas. Lake Tanganyika, which is about 600 kilometers in length, has a maximum water depth of 1,450 meters. Malawi has a maximum water depth of about half that. And it's important to recall that these two lakes together contain about 80% of all the surface waters on the African continent. So they're incredible resources for the riparian nations of the region. They're also particularly fascinating systems for the science community. They're truly island ecosystems. They're ancient lakes, of course. Lake Tanganyika might be more than 10 million years in age, and they're home to many thousands of endemic organisms. You can go to a single little islet in Lake Malawi and you can find species of cichlids that have evolved there or found there and no place else in the world. The cichlids are the most dramatic example of the endemism. Lake Malawi has more species of fish than any other lake in the world. But there's other remarkable exotic organisms in these lakes. The mollusks are remarkable. In Lake Tanganyika, you can find giant otters and electric catfish. These are remarkable biological laboratories. So these systems stand in strong contrast to the small eastern branch lakes, which are dominated by, which are comparatively small and hypersaline systems. These are generally, most of these lakes are freshwater and hydrologically open systems. Importantly for our drilling work, they're also, they experience the endless summer, so they don't circulate, right? The circulation is restricted to the upper 100 or 250 meters of water at the very most, right? So most of the water column in these systems is anoxic, and that at least helps preserve our sediment records very, very nicely. Furthermore, most of the biodiversity in these systems is really restricted to the margins, the shallow waters on the margins of these lakes. So the fault-related topography in these systems very much controls deposition and internal characteristics of the basin. So this is a Landsat image overlain on a DEM. It just illustrates how fault controls dominate these systems. This mountain range here on the edge of Lake Edward rises about 1,500 meters above the adjacent lake surface, and it's controlled by a single rift segment, a single fault segment. It has produced this pronounced uplift. In the offshore area on the hanging wall block of this normal fault, we have about 150 meters of water in this case, and on the order of 5 kilometers of syn rift fill. So these major faults, which are these pronounced features on the surface, must penetrate through much of the crust. Okay, and as a consequence, we've accumulated a tremendous amount of sediment, a long history of geological change in these basins. So before we go and sample these systems, we try to site survey the basins, just as is routinely done for ocean drilling projects, and we use systems that we deploy hydrophone arrays as long as possible behind our vessel in order to capture deep images of the subsurface. Now, unfortunately, these although most of these lake systems are navigable, we can't drive ocean-going ships there, so you guys get to use vessels like this, and most of the time we're stuck with operating boats such as this. Okay, so it's something that we've had to learn to adapt to over the years using vessels of opportunity. And I was describing to the students earlier a project we did for the Continental Dynamics program this past winter, which involved turning a 200-foot container ship into a crustal scale seismic survey vessel, and the not 7 plagues, but about 18 plagues that came along with that project, the non-trivial enterprise. So we generate subsurface images which allow us to position our drill cores, and this is just one legacy seismic profile which shows the overall morphology of the system. So this particular profile was collected in the northernmost part of the system, showing the asymmetric geometry of these basins, and this image of the footwall block, which again shows mountains rising up on the order of 1,500 meters above the lake, the adjacent lake surface, controls the subsidence of the system. Again, so we have on the order of 4 to 5 kilometers of syn-rift fill in the deepest part of this basin. So we have water depths of about 400 meters, syn-rift fill of 4 to 5 kilometers, and then a rift shoulder uplift of another 1.5 kilometers. So we have an incredible amount of displacement on the basement system. So these structures extend deep into the crust, and they're seismically active, and they, in the western branch of the Rift Valley at least, they generate very large earthquakes on average. So we've collected a series of nested seismic surveys to help us locate or position our drill cores in advance of putting together a drilling program. So I just want to show you a few clips of some of the high-resolution data that help to constrain some of the hydroclimate variability that we observe in this system. So this is a high-resolution seismic profile that's actually proven very useful. This and sister images. What we're looking at is an image of a lake delta that developed when Lake Malawi was on the order of 200 meters lower than present. And wherever these are a series of prograding cliniform reflections which are comprised of sand deposits, and they're being onlapped by organic rich muds in the offshore parts of the feature. Every time we collected a seismic image off of a river delta, we would find one of these delta cliniform packages. So we interpret this as being the topset foreset transition, or the subaerial to subaqueous delta in this basin. The geometry of these features are identical to what we observe around the modern deltas today. So the reason I put this up here is because these are great indicators for past paleo shorelines, and we can actually map out very clearly the past position of Lake Malawi shorelines. So what drilling can do for us is actually help us provide age dates for the timing of these much lower lake level systems. Here's another one of these progradational packages positioned in the northern part of the lake. This is the axial margin in this system, and this particular delta sits about 350 meters offshore. So we've got a series of delta packages that rim this margin at minus 200 meters, minus 350 meters, and even at minus 500 meters below modern lake level. And if we drop lake level this far, holding conditions of subsidence and sedimentation constant, represents a 98% loss in the volume of Lake Malawi. So it was a very different landscape when these features were being deposited. So here's just an example of a number of these features. So these come in handy when it comes to actually constrain our records from the drill core itself. And I'll come back to this because it's useful as part of our calibration exercise. So just one or two other geophysical images to help constrain the nature of the basin here. This is another river. This is a little fan delta that sits on one of these border faults, one of these rift shoulder margins. So again, this is the fault system. That we have a long segment here, 150 kilometer long boundary fault, which forms one of the major segments in the western branch of the rift. And we can see in blue a pronounced plume of water that is discharging from that fan delta. It's a rainy season image. And the other thing I wanted to point out here in this image are these little clouds. These are in fact lake flies, which are a common and important part of the biomass of the lake. It's actually not so much fun to have to drive your seismic ship through these. In our most recent experiment, we were encountering these constantly. they form, the lake flies erupt about once per month. That part of their life cycle is to emerge and mate once per month for a few hours, and then they die. But we actually find these in our drill core samples, right? It constitutes a pretty significant part of the biomass of the lake, and they're actually useful indicators, paleoecological indicators in many respects. So I want to show you just one or two seismic profiles off of this border fault margin right through here. Turns out there's a very complex channel canyon system that extends into deep water here. We have another border fault offshore in the form of a relay ramp. This is the bathymetric map of that area. So this is our long, relatively straight, faulted coastline. You can see in the bathymetric contours another break right here. This is a secondary border fault. We call this a relay ramp, so we have this structural feature in between onto which this river is dumping its load. Then we have a whole series of canyons and channels that extend off of this, eventually dumping material into the deepest part of the system through here. So this is a structurally very complex setting. We have done some coring and some survey work off here. One of the cores that we collected in this particular feature was in fact clean sand located 20 kilometers from the mouth of this river in 450 meters of water, just illustrating how effective these canyons are at delivering very coarse-grained deposits into deep water. So this is the modern system, and I won't show you all the seismic data that came along with this, but this is another profile that's adjacent to it, and we see a whole bunch of these acoustically transparent facies stacked up on top of each other. This is just the iconic symbol of my state for scale. So we're looking at several hundred meters of section right through here. So the question is, what is producing these acoustic cycles? Is it perhaps orbital precession, a common model for climate forcing in the tropics is as a consequence of changes in insulation due to precession, or is this system somehow forced by far-field changes in global climate, interglacial cycles. So it would have been great to just drill right through this sequence, except to drill very coarse-grained sediment on a lake in deep water would have been a very expensive and problematic endeavor, and such a core wasn't going to yield a sediment section, a fine-grained sediment section that would have been prone to a lot of the geochemical studies that we wanted